I'd love to introduce today Dr. Paul Moses. He's from the University of Oklahoma's School of Electrical and Computer Engineering, and he is currently working on some really cool topics related to uh, power stations and aurora. So, Paul, if you could tell us a little bit more about that, that'd be wonderful.
Sure. It's great to be here. Can everybody hear me? Or
Yes, thank you. Welcome. And also, we are kind of a very mixed group. So definitely, as much, um, well, keeping it more on the less technical side, but more on the explanatory plain language side would be fantastic as well.
okay, I'll try. I'll try my best to not get
Sorry for
too
the
in my
sorry for the
world.
warning there. No, we're good. We'll all work on this together. So
Okay.
thank you.
All right. I'll get started. So thank you for that introduction. I was invited to talk about some of the ground effects of the auroras, which affect the power system, namely what we refer to as geomagnetically induced currents. And I'm going to talk to you about some of the impacts on the power networks and some of the problems associated. But to make sure that we're on the same page, I want to start off with defining the source of this problem, which I think we all know is the sun, which is an enormous amount of electromagnetic radiation that is swirling around, and it finds its way to these sunspot regions, which are areas where the surface temperature of the sun is not quite as hot, but they're associated with very strong magnetic field activity, and the magnetic fields around these sunspots are so strong that they restrict the natural heat convection process. That's why it's a little bit cooler, although it's still hot in those areas. So that is the source of the problem, and that's where the source of the electromagnetic radiation starts from. And some of you are probably more aware about the space weather phenomenon than I am, but the solar flare activity that surrounds these areas is an explosion of electromagnetic energy that's around the sunspot area. And these charged particles propagate these intense, very intense magnetic fields that flow through space, as you know, space wind or solar winds. And they're accompanied by what we know, what's termed as coronal mass ejections, which are large bubbles of charged particles and EM radiation. And when that interacts with the Earth's magnetic field, when that space wind hits the Earth's magnetic field, it causes it causes a ground effect, which I'm going to describe in a little bit more detail, that affects the power system. But as you know, they also trigger these CMEs, coronal mass ejections, trigger the auroras, and and I'm going to talk to you about the interference to the electrical system. So this picture describes the cause and effect of the whole interplay that happens between the auroras and the ground. So as I said, these solar winds perturb the magnetic field of the Earth, and there are actually in the atmosphere electrical currents that flow along the magnetic field of the Earth in the ionosphere, and the energy, the electromagnetic energy that's inside, that's associated with these currents, disrupts the magnetic field in the Earth. And that's where you have a transference of energy or interaction with the Earth, where there's an action when you have a change of magnetic field, a time varying. Some of you might be aware of Faraday's law. When you have a time varying magnetic field, it induces a voltage on a coil. So that phenomenon happens also from the atmosphere to the Earth. There's an induction process that induces on the Earth an electric field, which is if you like, a voltage of some sort that's dispersed along the ground in certain areas where there's low conductivity, we say, or high resistivity, certain rock geologies like igneous rocks, formations of the Rocky Mountain, these electric fields can concentrate around those areas. And if these electric fields are large enough, they can, as you might be aware, when you have a large voltage, it's going to push a current. And that current is what we call geomagnetically induced current, GICs. And that can flow along certain soil types and metallic structures like pipelines. And where it enters the power system is the transformers. You might be aware transformers are the devices that change the voltage level from one level to another level. And we use transformers all over the power system, and they're grounded. The windings of these transformers are grounded, physically connected to ground, and that gives the opportunity for GICs to enter the power system through that ground connection. So it's quite remarkable, but there's a lot of these ground connections, and there's a lot of opportunities for GICs to enter the system. And it's the type of current that flows is like a DC type waveform, like you might be aware of a battery has a very steady level of current. Well, the frequency of this current is so low, it's sort of like we say it's DC. And the power system is designed to operate on alternating current. So you have a mix of AC and DC, which is not very good. And I'll describe those effects later. So when did we first notice this effect on in my field, electrical engineering? It wasn't power systems. It was actually the telegraph system, which predates power systems. Before we had electrical power networks, we had communication lines through telegraph lines, which was the first man-made electrical network used for communications back in the 1800s. And there was a major storm in 1859 that affected the telegraphy network, known as the Carrington event, and it caused a lot of disruption to telegraph stations. And since then, there have been disruptions in the early part of the 20th century like that have affected the communication systems. Less so now because we've moved away from telegraphy, and conductor power telephone lines are now fiber optics, so we don't have that kind of effect anymore. But that was when it was first in my field in electrical engineering, we took notice, and literature started to appear on this topic in my area. Here's another view of the phenomenon. These auroral currents that, as you know, causes those lights in the sky. They induce on the ground these ESPs, Earth surface potentials, which can be from the range from 1.2 to 6 volts roughly per kilometer. So it doesn't sound like much. That's why nobody gets electrocuted, because the voltage is so low for a small amount of distance. But when you have a large power line, long distance power line, that voltage can build up across the power line if the electric field is oriented correctly. That can be several hundreds of volts, which can cause this GIC to flow. And so there's a concerted effort, which you might be aware of, by the US Geological Survey and National Oceanographic and Atmospheric Administration to track where these ESP are along the Earth's surface and map them. And so there's magnetic observatories, if you like, that try to measure these ground effects and try to work with utilities on where the vulnerable locations are. Because if power infrastructure is located in these regions of ESPs, that's where you have the problem. Okay, so here's a little bit more detail about the power system. The power system power line transmission system typically have transformers on both ends of the power line. So this is the transmission line, which is overhead transmission line, and these are the step-up transformer at the source and the step-down transformers at the load side near substation, which are in substations. And the flow of current, so you have this GIC current in the ground, flows into the transformer through these, we call them neutrals. These are grounded for safety reasons and for protection reasons. We have a ground connection at these points. And these are the entry-exit points of GICs. And now what you have is a DC current superimposed on an AC waveform. And the power system was not designed to the transformer was not designed to operate. It was in that manner. It was designed to operate on alternating current without a DC component in it. So this DC current, as I mentioned, is very low frequency. And the GIC that can flow can range from tens to hundreds of amps along power lines. And the power line itself is carrying the normal load of the current for the load that it's serving. Now it's also called to carry the load current plus the GIC, and that can cause very detrimental effects, which I'll go into.
Could you say these long transmission lines mostly that are susceptible, are they mostly the east to west ones?
Yes, so certain orientations are of the lines more vulnerable, like east to west. You're right, because of the orientation of the magnetic field lines on the Earth.
Yeah. Yep.
Yeah.
Okay. And yeah, that's kind of from the physics, as well as when you think about some of the big events in the past, the telegraph wires that were affected, cross-continental.
Exactly. So that's right. I'm noticing some questions in the chat window. It's hard to keep an eye on that. But yeah, feel free to speak up if you have any questions as I go along this. Here's a measurement of a particular GIC, a particular transformer in one of the components in the Con Edison utility. And you can see over several hours how it fluctuates and changes polarity, positive to negative, coinciding with the storm activity. So when did we first take big notice in the power system industry? Was when it hit the Quebec, Canada power system. That was the worst power disruption that's happened so far. In 1989, there was a geomagnetic storm that you might have been aware of, and it caused an over 8-hour blackout and many transformers to be damaged and overheated. And since then, there have been several events that have happened in South Africa, Sweden, New Zealand, and UK, where transformers were damaged, but none as bad as the Quebec, Canada scenario, which really woke up the industry to take notice that this can cause very widespread impacts to the power network. So it was not just the transformers that got damaged. There were other components like capacitors, and so a question: do GIC type issues cause dramatic reaction, or they just shut down? Some of the impacts are sudden, but a transformer might fail over maybe many hours or even several days later because it's already been stressed by the heating. So some of these effects from GICs may not be immediately apparent. They take time to see the impact, because transformers were designed to last for 40, 50 plus years. And if you overheat them, that severely cuts down their lifespan. So you may not see these effects for many months to come. But in the Quebec, Canada situation, the effects were quite fast. It was a very big storm, and the storm caused failures that very day. People often ask if transformers blow up. They're pretty hardy devices, so they overheat and then they trip off the line. There are protection devices that if there's a fault in the transformer, they are taken out of service before there's any serious catastrophic explosion. But there have been explosions, but as far as I know, not to GICs. The temperature rise is usually trips off the transformer before a severe explosion occurs. So here's a typical transformer, high voltage transformer. Just so you're aware, these transformers can have voltage ratings from 230 kilovolts to 345, 500, 765 kilovolts are the more common transmission level voltages that we use. And these are located at substations. Inside the transformer, inside here, you have a magnetic core and windings that are wound onto that core. And the magnetic core has a magnetic field. A transformer operates by an alternating magnetic field. From Faraday's law, you have an alternating magnetic field that generates a voltage according to the number of turns, coil windings. So the magnetic field propagates in this core. It also comes out of the core and flows through the tank in the air. There's a component that flows there. Now, when you have GICs, in this next slide, this is what we call a magnetic circuit. It represents the flux, the magnetic field that flows in the core. And you can see that there's now an anomalous DC component. This GIC is creating a DC magnetic field when it's normally supposed to have an AC magnetic field, alternating magnetic field in the core, magnetic core. And that causes the transformer to draw a very distorted current. So the GIC that flows through the transformer distorts the magnetic field, and it causes the magnetic field, the transformer, to draw what we call a non-sinusoidal current. And I'll show you that in the next slide coming up, how that current looks like. But it causes overheating, harmonic distortion, vibration, audible sounds, and malfunctions. Here is how those currents look like. Now, this was done in my lab on a set of transformers. So let's look at the left here. You can see for a range of GIC that we artificially injected. Normally, the current is supposed to be centered around for a particular. So I have three windings in that transformer, and the current is supposed to be centered around the zero axis. But when you have GIC, increasing GICs as you get into the red region, that waveform gets shifted up. The current, alternating current, gets shifted up and gets peaky. You get these very large, sharp peaks that very large enough to cause overheating and damage to the windings of the transformer. And it also happens in the reverse direction, the negative peaks. And this causes harmonics. So this is a harmonic spectrum of these currents. And normally you're supposed to only have this, this component, 60 hertz. So this is the 60 hertz. The power system operates on 60 hertz frequency. The alternating current has a repeating waveform every 60 cycles. But when you have harmonics, you have these other frequencies, like musical tones, if you like, that appear as distortions in the waveform. And they cause overheating, and the transformer and the power system was not designed for this. Just quickly, you're aware of the transformer there's not one single type of transformer. There are many different types of transformers, how the windings are wound and how the core, magnetic core, is arranged. And they all behave differently. They all behave differently to GICs. So the question, what level of current was used in that test? I went up to about 40 amps of DC current. These transformers were small scale to scale, but smaller transformers, and we didn't dare to go more than 40 amps because we didn't want to cause any accidents. So we were pretty cautious when we did these tests because we didn't know what would happen. So we went 40 plus and 40 minus DC amps. In reality, on the bigger transformers, you can have hundreds of amps of DC.
Thanks.
So there's many types, and this is a challenge in my field, is that how do we model if we're modeling this phenomenon, we have to make sure we're modeling the right type of transformer, and they all behave differently. There are impacts on the system protection for those of you who are not power engineers. If you take a transmission line, they are often monitored. They are always monitored by these things that we call protection relays. They're monitoring devices on both ends of the line that look for short circuits on the line. And if there is a problem, they take the line out of service. So they are looking for overcurrent and abnormal operation of the power line, but they are not set up for monitoring GICs, which is one of the issues in the power industry. They don't detect them, and sometimes they maloperate. With the GICs, as I said, these harmonics here that you see in this waveform, when that flows through the measuring devices, they cause errors and maloperation, because you don't want to unnecessarily trip a line off, to take a line out of service, because the load that line was supplying will be transferred to another line, and it might get overloaded, and then that line will trip off, and then that load is transferred, so on, and you get a cascading failure. So tripping a line off unnecessarily is unwanted. So GICs have the potential and have caused these protection systems to maloperate because of the harmonic distortions in the waveforms and the errors that they caused. So what are we doing about this problem in the industry? FERC, which is the Federal Energy Regulatory Commission, who are like the policing, they police all the standards that utilities must follow. They mandate utilities to take certain due diligence precautionary measures to make sure that there are no unnecessary risks that they're taking. So one of the standards that they created was specific to this disturbance, to develop standards to mitigate geomagnetic disturbance on power systems. And that's basically forcing utilities to make sure they're doing ongoing vulnerability assessments of their the transmission system owners have to develop plans and submit these plans to make sure that they're doing their due diligence. And some of the plans may look at how do analysis on how the transformer behaves thermally, how to monitor GICs in their system, how to block GICs, and develop new system models to do what if scenarios if a GMD like the Quebec scenario happens. Is the timing of these plans on time for solar max? Well, the planning, it's definitely to do with the frequency of these events. That Maxim understands. So they have mandated that the utilities have to do these on an ongoing basis every, I think, 60 calendar months, every 5 years. they have to update and revise and continually improve their planning to mitigate against these solar disturbances. So GICs are very infrequent events, but they're high impact. And as we saw in the Quebec scenario, they can be very widespread. But that was enough to cause the industry to develop these plans and make sure utilities are in compliance. So these are some of the effects I already mentioned that they're trying to make sure that they are prepared for if it occurs in their power systems, transformer overloading and capacitors that might fail and harmonics and so on. They have to make sure if these occur, can their system withstand it? If it does, can they somehow, if they lose a line, if they lose a power line, can the system still operate without causing blackouts or cascading failures? So some of the solution approaches is installing blocking devices. Now, we saw this circuit before. Is there a way you can install a filter that'll disrupt the path of these GICs? And the problem with that is it's not gained widespread industry acceptance because by disrupting this, disconnecting this this neutral from the ground, you're defeating the purpose of grounding that, which is for protection and safety reasons. We keep the power system grounded. So there's not a lot of industry buy-in yet about using these in the system because it actually can compromise the normal operation. So there's limited implementation of these devices in the network. Plus, if you do block the flow of this GIC in a particular line, you may inadvertently redistribute the flow of that GIC to another neighboring line. So you block the current here, but it finds its way into another line that you didn't anticipate. And that's the same issue as preemptively removing a transformer and a power line out of service when you know there's a GMD event happening. Can we protect the transformer from damage and take it out of service? Yes, but you might cause this redistribution of GIC. Could you stick some kind of battery near to collect GIC energy? I don't know about that. That's beyond my thinking. Using it as, I don't think that the energy is there for that long to be of any viable use. It's not something that's predictable and reliably that could be collected and used. So those are the main solution approaches, and identifying regions of high risk areas that if you do lose a line and you have a high risk of cascading failure, protecting those lines, diverting resources to those lines to make sure they're properly monitored for GICs. Because right now, very little of the power system is monitored for GICs. It was not set up to detect GICs. The other thing is to look at the transformer capability. If the GIC is not so severe, keep that transformer running, even though there is GIC flow, but it can handle it without having to take it out of service. So there's a lot of work being done in the industry to decide on transformer operating limits with GICs. And if there is a GIC in a transformer, lighten the load on the transformer, readjust the system so that the transformer does not get overloaded and fails. Because these transformers if they fail, they take upwards of over a year and a half to order and replace, because they're very long lead replacement items. So damaging a transformer is a very serious business. So I think I'll conclude by saying that GICs in power systems are very real and significant threat, and there has been a big precedent with the Quebec scenario that looms that might happen again, and it still is difficult to detect. So if a GIC event occurs in the power network, it may have already caused irreversible damage in transformers and other components before any mitigation can be done. But the industry is trying to is making great efforts to improve the situational awareness, find out where the vulnerable locations are, install proper measurement devices, and working on research on effective blocking strategies. And the newest area which I'm working on a recent NSF project that's got funded is, what about renewable energy? Because the power system has fundamentally changed since the Quebec scenario, since the 80s. Power system has grown much more expansive, and it's got a lot more newer technology with renewable energy, wind farms, solar farms. And there's not a lot of research that has been done yet on how those technologies will function with when you have GMDs and GICs in the system. With that, I'd like to conclude and thank you for listening. And if you have any questions or comments, feel free to ask.
Thank you.
Thank you so
Oh,
much.
go ahead, Liz.
Oh, just to say thank you and congratulations on your grant as well. That's really exciting. And it's a little disconcerting that even though there's new regulations and like the power industry is keeping an eye on this, that maybe there isn't enough research being done on the new grid systems. And of course, it's also great to yeah, kind of connect to the space physics industry as well, and this industry, you know, connects to all different space weather, connects to all different industries. So it's great to learn a little bit more about how it connects to the power industry.
Thank you.
Do we have some questions from folks?
I think one of the questions that that we get fairly often is, would this affect my cell phone or my computer or small electronics, my car, things like that? Do GICs affect those?
I don't think so, because it could affect the if there's a power system failure and it affects the cell phone coverage network, which is powered from the power system, but they have backup systems and generators and so on. So I don't know about the magnetic effects on the cell phone wireless system. So it's possible, but that's not really my area, wireless communications. But if the power system is disrupted, that could potentially disrupt the powering of these cell phone communication stations and towers.
That makes a lot of sense. Thank you.
Yeah, it's usually a long transmission line kind of thing. I was wondering if there's any reason that like solar farms might be more vulnerable, given that, or yeah.
Yeah, one of the things, the solar farms, they're connected to the grid via these converters, power converters. Because solar is DC, the grid is AC, so you need a power converter in between. So one of the research topics that I'm working on is how GICs may interfere with the operation of those power converters, which, as far as I know, there's not been much work on understanding how they operate when you have large GICs. So far, a lot of the research has been on a power system without renewable energy in it. We know a lot about how transformers behave and how the power line and protection systems, and there have been changes, but the renewable energy is still a new paradigm. That's large unknown risks with GICs.
Maybe we would find that that was a source of free power at night. The solar panels would generate some power. I'm not sure.
Right.
I mean, telegraph wires did that during the large 1859 event and then also burned up. So,
right.
yeah.
I have
One
a
question.
Go ahead.
Yeah, Michael.
Yeah, so one question from my side. What can be done to protect the power grid if you know that a severe ICME is heading directly towards Earth? So if you know that's a high risk that something will happen, how can you, or what can you do in advance to protect the system? So do you cut off lines in advance, or just waiting until the currents get too high and then cut lines? What is the concept, and is there a general concept for the, let's say, United States, or maybe you know it for Europe? So is there a consensus between different companies operating the grid? What have to be done, and how do they have to communicate to each other to do to act yeah, in in a way that the whole grid is protected, and not just a part of a grid from one company?
Right. So yeah, the reliability, the Federal Energy Regulatory Commission, they are mandating the utilities to make sure they have they call it contingency planning. So they play the what if, always they're playing the what if game. If a power line is taken out, the system has to still operate. So they operate on what is called the N-1 contingency. If they lose a major component, like a transformer or a power line, the grid must still operate normally without any blackout. So they have been, if they know in advance a GMD disturbance is imminent, they will readjust the grid operation, generators, the dispatching of generators and so on, and the load, so that if a line is taken out of service, there won't be any detrimental impact. But this is getting more difficult, because if it coincides during a time when the grid is very stressed, like a hot day, and the load is very heavy on the grid, taking out a line, a critical line, is not always an option, because that load will have to be met by the other lines and they get overloaded. But the utility has already has contingency plans. So if, to a certain extent, to redispatch generation, switch lines out of service, and also know what the operating limits are, like the transformers. How long can they withstand an overload without causing severe damage? So I would say that those are the main methods. And they're doing a lot of system modeling right now with playing the what if game with GMDs. If a GMD takes out this line, what will be our plan to readjust the system? So that's what's being done right now.
Okay, thank you.
Are there any grids that might be particularly vulnerable to GICs, considering maybe the age or configuration of the grid, but also the ground that it covers?
Mainly in the polar regions, and long transmission lines in the polar regions have, as like the Quebec scenario showed us, were most vulnerable, because the higher the voltage, the longer the lines that they use, and the longer lines are the ones that are most vulnerable. But we can't avoid that. We need the long transmission lines to carry the energy where we need to go. So it's the long transmission lines and in the polar regions that have seen more risk.
Thank you. I have a question for you, and Liz, you can chime in on this if you want to. So Aurorasaurus is a participatory science project that tracks auroras through reports from anybody who sees auroras. but other projects also analyze data or gather data, things like that. Are there opportunities for participatory science or citizen science to help model or figure some of this out?
Oh, I'm sure there is, because the power industry gradually they're trying to work with multiple agencies like NOAA and the Geological Survey, and to try and better map these regions and get an early, that's the priority, is trying to get an early warning system of GMDs occurring. And I'm sure there are they would welcome some input on how to early detection of this phenomena, and once they know that, brace the power system once an event is imminent.
I've got a question.
Yeah, I think I would add just slightly that some of the citizen science, tracking of auroras is very near real time, but it's also maybe more better knowledge of where the aurora is overhead than some of the models, and when it's really dynamic and active, that's when some of these other sources of data can be the most valuable. And then there's also a bunch of different commercial off-the-shelf magnetometers and denser arrays of magnetometers that are being fielded by different groups. And I noticed I think I pulled up the FERC something or other page, and it talks about magnetometers as well. So there might be some possibilities there.
Right.
Donna.
Is the system more vulnerable at dawn and dusk, wherever dawn and dusk is, if it hits there? The reason I ask is because of some things I've heard Dr. Tabitha Scove talk about, how the magnetic field is concentrated at the magnetic field lines concentrated at dawn and dusk, wherever that is on the Earth. So would that play into this?
Well, that I'm not sure about, but because I know in the power system, when we had these GIC events, they happened at any time of the day, not particularly dawn and dusk. So I don't think there was a major correlation with the time of day, but I might be mistaken. I'm not sure about that.
Okay, just curious. Thank you.
It's a great question, Donna. I was thinking, they might be more prevalent at midnight, because the aurora is the strongest there. But yeah, there probably are some there. We can take that and see if we can find some papers on the distribution of GICs and local time with respect to the sun-Earth system and the Earth rotating.
Speaking of the distribution of GICs with regard to the aurora, do they most frequently happen under the auroral oval, or how would they track with like the view line for how far you can see aurora? Do they spread out further than the auroral oval, or are they usually happening underneath it?
They spread out further, and the perturbation of the magnetic field is what's key here. So it's not just the auroral currents and is underneath it. It distorts the whole the magnetic field of the Earth, and that fluctuation in the magnetic field is very irregular, and it can cause those Earth surface potentials to appear. Interestingly, like I did mention, the polar regions are most vulnerable, but they're moving to lower latitudes. That's why there has been studies that's shown that they're at risk as well, and it can be far away from those auroral latitudes, but there's not been a lot of occurrences, but the risk is still there, and that's why the utilities are saying all utilities in America have to submit plans, not just the ones in the polar near the upper latitudes. All utilities need to submit plans of their vulnerability assessment. So that's my take on it.
Thank you. Do you have any other questions? Liz, you're talking, but you're
Sorry, I had one more. I think I saw somewhere that your grant included some educational outreach, and I was wondering what that was.
Yeah, for NSF projects, you have to build those in, and I want to. In my area, there's not a lot of awareness about these disturbances in power systems at in early education. So I want to reach out to. In fact, our industry is really suffering from power engineers, we call them. There's a lot of them retiring, and we need to make people more aware about career paths in the power industry. And one of the ways I want to do that is to make them aware about how these weird disturbances can cause these bad effects in power systems. And I think that would be something that would appeal to very early education, because it's something they know what the aurora borealis is, but they're not aware about the unseen effects on power systems. So I think that's a good opportunity to hook people into my field and build some new talent. So we want to go into high schools and K to 12 and talk about these phenomena and career paths. One of the things I want to do is be able to build a very low cost power system model they can build, and show them how a power system operates and what happens when you have a disruption and the lights flicker and so on. So I think just building awareness about something we take for granted is electrical energy too easily. When it's not there, we notice, but it's like that's what I want to impart.
Excellent, thank you. And now that we've met, if you have any interest in learning more about nitty-gritty of auroral storms and what happens when the sun's energy, you know, connects to the Earth's magnetosphere, and how there's a lot of complexities there. So, and we really enjoy the outreach aspects. So anyone is welcome to join us as well.
That's great. Thank you.
Thank you so much. This has just been fabulous. This is something that we get a lot of questions about, and I haven't really had a good sense for how to answer them. But you have really opened my eyes into how this works as a non-scientist, and I'm very grateful for that.
Oh, thank you. Thank you so much.
Great.